Homework last night, page 592, we had 1 to 2, 5 to 8, and 10 to 16. We got a list of 5 questions that we need to go over here today. Looks like the latter bunch of questions were the challenging ones for us. We got 10, 11, 12, 15, and 16. Let's take a look at number 10 here first. A qualitative question. It says list 2 differences and 2 similarities between gravitational and electric fields, gravitational and magnetic fields, and then electric and magnetic fields. So the 3 types of fields that we've learned about this year. Really gravity was last year, I guess, but electric and magnetic fields this year. Let's compare and contrast them. Tell me a similarity or difference, I don't care which one it is, between gravitational and electric fields. What's one, either similarity or difference, and then tell me whether it is a similarity or difference. Rucker, what's one?
Gravity relies on mass.
Okay, good. So gravity is caused by mass. Electric field is caused by charge. That would be a difference, obviously, right? Good. So we got one difference. Give me another one. Another difference or a similarity. I don't care. Okay, so they can both be attractive, but electric can also be repulsive. So there's a little bit of similarity there in that they can both be attractive, but the fact that electric can also be repulsive, that's a difference, right? We're kind of combining a similarity and a difference there. Rucker talked about what causes an electric field and a gravitational field. What about what experiences a gravitational and electric field? What kind of object would experience a gravitational field? Well, it would be a mass. What kind of object would experience an electric field? It would be a charge. So what produces it is different. What experiences it is also different. The direction is also different. So we got 3 differences there. What's the similarity? Good, they're both vector fields, so they both have a direction associated with them. Even though the direction is different, they both have a direction associated with it. Good. What's another one? What's another similarity? How about the shape of the field? The shape of the field. We call them radial fields. Here's the gravitational field surrounding the Earth. Here's the electric field surrounding a charge. Now, its direction could be different, right? It could be outwards or inwards depending upon what kind of charge it is. Let's say it's a negative. Okay, electric field is pointing inward. The shape is the same, right? Anybody think of another similarity? I think we listed 3 or 4 differences there, 2 or 3 similarities between them. Those kind of things are the things we're looking for. Let's take a look at B and see if we can now knowing the answer to question A, or at least part of an answer to question A. Let's see if we can go through B a little bit quicker. What about similarities and differences between gravitational and magnetic fields? A lot of these we can repeat, right? Brad? Okay, both are vector fields. That's a similarity. Good. Okay, so magnetic fields can repel or attract, whereas gravitational fields are only going to attract. Okay? Yep. Go ahead. Right. Okay, again, what causes it? Gravitational fields are caused by mass. Magnetic fields are caused by magnets, right? Ferromagnetic materials that have domains aligned are magnets. One of the things I forgot to mention with the electric fields and gravitational fields, you guys forgot to mention this as well. We know that a gravitational field is generally a weak field, right? Whereas the electric fields are generally stronger. Magnetic fields would be the same. Magnetic fields tend to be a stronger field than a gravitational field as well. Electric and magnetic fields, both vector fields. They can both be attractive or repulsive. There's a couple similarities right there. One's caused by charge, one's caused by magnets. There's a difference. A magnetic field has to exist between 2 poles, a north pole and a south pole, whereas an electric field can exist as a result of only one charge, either a positive or a negative. It can exist as a result of 2 charges. Okay, like a magnetic field has to exist as a result of a north and a south, but the electric field doesn't have to. Yep. Yeah, you know what? You got to be careful with that record. That's a whole different thing. You're talking about something called the electromagnetic radiation. And electromagnetic radiation consists of an electric field and a magnetic field. So that's not so much comparing the electric and magnetic field. That's talking about, you almost say a third thing. Right? There's electric, there's magnetic, and then there's this electromagnetic radiation, which consists of both. So I don't really want to go there with this discussion. We will go there later on, but not with this discussion, okay? Yep. Yeah. Yeah. All right, let's take a look at number 11 here. Yeah, using the domain theory, explain the following observations. A magnet attracts an unmagnetized ferromagnetic material. Well, remember that an unmagnetized ferromagnetic material has domains pointing in pretty much random directions, right, or seemingly random directions. Why does a magnet attract something that has domains pointing in random directions? What does it do? What effect does it have on these domains? Hayden? Good, good. It temporarily aligns those domains. Kind of like when we talked about charged objects attracting neutral objects, we induce a temporary separation of charge. Here we're not separating anything, but it is still a temporary alignment. We're inducing, again, a temporary alignment of domains instead of inducing a temporary separation of charges. Stroking a nail with a magnet magnetizes the nail. Well, same kind of deal, right? We're temporarily aligning the domains in the nail from the magnetic field that's caused by this magnet. Metal table leg affects a compass. Why would a metal table leg affect a compass? Yeah, assuming it's a ferromagnetic table leg. Yeah, again, it's basically, it's like the answer to question number A, right? A magnet attracts an unmagnetized ferromagnetic material. Well, a compass is a magnet. And the unmagnetized ferromagnetic material here would be your table leg. So it attracts it. Because it temporarily aligns the domains in the table leg. Yep. Yep. Yes. Yes. The effect is stronger for sure. Yeah. Number 12. Why does dropping or heating a bar magnet decrease its magnetic properties? Yep. Yeah. Yeah. Basically, that's it. Basically, the more kinetic energy you got, the less chance of these domains being aligned, right? They start scrambling, right? If you get a whole bunch of people, an analogy here, it's not a literal thing, but an analogy here. If you get a bunch of people lined up, okay, lining up, to go to a concert or something, and you put a whole bunch of kinetic energy into that lineup, maybe it's really, really hot, or maybe, there's a loud noise or something, and it gets people scattering, right? People start moving all over the place. When you add kinetic energy to that line, though, it's no longer as good of a line. It's no longer as straight of a line. When you add kinetic energy to it, it scrambles things. And that's why dropping a magnet or heating a magnet scrambles the domains and takes away, at least to some degree, the magnetic effect. 15. Do magnetic fields always run parallel to the surface of the Earth? Yes or no? Forget about the explanation right now. Yes or no? No. No. We do a picture of the Earth's magnetic field, right? In fact, there's a picture of the Earth's magnetic field right above it. Some of those look pretty much parallel to the Earth, right? Right in here, they look pretty much parallel to the Earth. Not exactly, but close enough. But up here, they're not even close. They're pretty much perpendicular to the Earth's magnetic field at the poles. And then, of course, somewhere in the northern reaches of the Earth and the southern reaches of the Earth, it's going to be somewhere in between parallel and perpendicular. But the bottom line is no. No, they're not always parallel to the Earth's surface. And my explanation would be, see the picture, see the diagram. Clearly, some of the lines are not parallel to the Earth's surface. Some of them are perpendicular almost. Yep. Is that right? Yeah, which Just question number 14 right there, right? You guys didn't ask me to go over question 14, but that addresses that right there. Why is it difficult to get an accurate bearing with a compass needle near the poles? Well, because you're holding this compass like this, right? You guys, in that little activity we did with magnetic fields early on in this unit, you guys held the compasses near the magnets. Well, the compasses point horizontally, parallel to the Earth's surface. Now, if the Earth's magnetic field isn't parallel to the Earth, then the compass needle is going to have a tough time reacting because it always has to point parallel to the Earth. Well, if you're at the poles and the field lines are virtually perpendicular, well, then the compass needle can't point downwards unless you have a different kind of compass that can act in 3 dimensions, right? An X, Y, and a Z axis, as opposed to just X, Y. Yep. Okay. Okay. So it's still attached some way on something. So yeah. Okay. Okay. Fair enough. Yeah. Let's take a look at 16. The last question here. If a current carrying wire is bent into a loop, why is the magnetic field stronger inside the loop than outside the loop? I like this question actually. This is a good one to finish off with. It's a bit of a tricky question, but I think it's a good question, a good understanding question here. Okay. Who thinks they have an answer to that? If a current carrying wire is bent into a loop, why is the magnetic field stronger inside the loop than outside the loop? So what we're saying is, look, I'm going to draw. We don't necessarily have to have that piece of steel or iron inside this, but we're going to draw it because it makes it a little bit easier to see the loop if I do that. Right? You can see the representation of the loop a little bit better if I draw something inside. Remember, we don't have to have it inside. Why is it stronger? Why is the magnetic field stronger inside that loop, or where that piece of steel would be, rather than outside the loop, right over here? Yeah. Why though? Why would the? Yes, yes. I think you got it there. Okay. If we take a look at, let's say this is a wire. Okay, this is a wire, and we look at the magnetic field surrounding this wire, and we look at it directly to the left of that wire. So this point right here. Okay, this point right here. We say thumb in the direction of the current, which is up toward the ceiling, right? Fingers, well, we want to put our fingers directly to the left of that wire because that's where we're trying to find the field strength, right? Pointing in this way, right? Make sense? Okay. This way it's to the right of the wire, it's pointing outwards. Got it? Okay, if we have a wire right here, okay, and you've got a magnetic field pointing at this point towards the front of the room or inwards, and then you have another one right here pointing this way, and then you have another one right here pointing this way, then in effect, outside to the left of that wire, you're going to get a magnetic field that looks like this. Right? Magnetic field right here pointing this way, here pointing this way, here pointing this way, a net magnetic field pointing this way. Okay. Now, on the other side of that wire, it's going to go the other direction, right? It's going to go this way, this way, this way, this way. Same deal, right? You're going to get a magnetic field like this inside the coil. Here's my coil. But let's take a look at the other side of the coil, or even a quarter of the way around the coil. Outside of the coil, right? This was my first loop of wire, okay? This is my second loop of wire over here pointing in the opposite direction. Outside, I get a magnetic field pointing this way. And then inside, I get a magnetic field pointing, which way was I? This way? I kind of get my hands messed up here. But the bottom line is, if the blue represents the wire here, the coil, oops. If the blue represents the coil, then you're going to get a magnetic field outside the coil all around it, but it's going to be distributed all around it. Inside the coil, you're going to get a magnetic field as a result of all of the wire, but it's going to add up. It's going to be, in a sense, constructive interference. Does that make sense? So this magnetic field right here isn't connected or interfering with or adding to the effect of this magnetic field right here. But the magnetic field inside the coil caused by this wire is is going to interfere with or is going to constructively add up with this magnetic field. So it ends up being stronger here, you end up with twice the magnetic field. The reality is it's not just over here and over here, it's all the way around, so the effect is even bigger than it would be if you had just two sides. Yep. Yeah, in a sense, yeah. Yeah. I mean, each part of the wire produces a magnetic field, the same magnetic field. But inside, you're getting the magnetic field caused by part of the wire on one side of the coil, part of the wire on the other side of the coil, and the magnetic field is in the same place, right? Whereas outside of the coil, it's in two different places. Yep. Yeah. Let me think about that for a second. So you're saying it's kind of like a slinky when you wrap it around in a circle. Yeah. I'm not sure if we could use that analogy or not. I'm not sure if that would work or not. Yeah, I think I need a little bit more on that, like, a little bit more on your thought on that. Yeah, I'm not sure if I like that one or not. I think I'd need a little bit more from you, and I think I'd need a little bit of time to think about that one too. Okay. Yeah, in the sense, yeah, because in the end, we're talking about something that's produced by, right? Like if I take this is my coil, then let's look at right here, this spot right here. Okay, it produces a magnetic field, let's say pointing this way. Okay, inside it produces a magnetic field pointing this way. Well, on the other side, it produces a magnetic field pointing this way and a magnetic field pointing this way. So we've got the magnetic field outside caused by this wire, the magnetic field outside caused by this wire, but the magnetic field caused by both of those wires inside is constructive. It's both in the same place. And I'm not sure if your analogy quite works there, because you're almost saying the wire itself is denser. Right? Unless I'm just not quite understanding your. Okay. We'll chat about it later if you want to add something to it. Okay, guys, we good at this? It's a tough question, but does it kind of make sense to people? I don't know if I explained that well or not, but hopefully it makes a little bit of sense to you at least. Hopefully you guys had some kind of, grasp of that. Even if you maybe gave an analogy that wasn't quite perfect, that doesn't mean that your thought wasn't, that you weren't thinking quite the right thing either. So, yeah. Okay.
Now, like 2 centimeters diameter and one pipe is really like 6 centimeters. One fills the basin of water, the other answers it, but the basin's volume never changes. The same pipe has to have a lot higher velocity of the water, which is like a lot more magnetic force.
Yeah, I'm not sure if I like that analogy either.
I just wanted to know.
Okay. No, but hey, you know what? I say I'm not sure if I like those analogies. It's not that I don't like the thoughts. I do. I do like that you guys are thinking about things in a different way like that. I do, even if they don't quite work perfectly. We can add something? No? You looked like you were ready to say something there. No? All right. Guys, I want to do a couple multiple choice questions here right now, okay? Number 66 in your multiple choice booklet. Have a look at that, and you're going to submit that one, please, as multiple choice number 1 on your phones, please. Let's take a look at this here, guys. You guys have submitted your responses, and you've done fantastic on this question. We've got a bunch of shapes of magnetic fields here. Polarity of these magnets not labeled at all. We're not going to panic about that because we have direction, we have shape. We could easily figure out what the polarity is based on the direction and based on the shape of the magnetic fields. The question says, given the magnetic fields illustrated above, the magnets will repel in which diagrams? We actually don't even need to have the polarity labeled to answer this question. Okay, we know the answer to this, right? All of you that submitted an answer picked D. Does anybody want to volunteer why you picked D? It's correct, right? But why did you pick D? Go ahead. So that would be 2 and 4, right? Go ahead. Good, perfect. Diagrams 2 and 4 show field lines being pushed apart. Here, we have field lines coming together. We don't need to have the polarity of these labeled, although we could go through and label the polarity of these pretty easily, right? This would be a north end, this would be a south end, because field lines are going away from the north and toward the south. We don't need that, though. In the end, if field lines are joining up from one magnet to the other, there's a force of attraction. So it can't be number 1. Okay, it also can't be this one because you have field lines once again joining up with each other right here. We could label this as a north pole, this is a south pole, this is a south, this is a north. Hey, that'd be fine. We don't need to do that because field lines are joining up. We know it's going to be attractive. Okay, we take a look at this one. No field lines are joining up. We could label the polarity here, north, north, south, south. But again, we don't need to because the field lines are repelling each other. Same deal here. Field lines are repelling each other. So both of these are going to work out for us. 66D. Good. Excellent. Let's take a look at another multiple choice question now. Multiple choice number 68. This one should remind you of a multiple choice question you had on your last test for electric fields. Okay, this is magnetic fields. Okay, but it's very, very similar to a question that you had on electric fields on your last unit test, and then even as a practice one prior to the last unit test. All right, for this one, 79% of you have said D, and the other 21% of you have said A. So kind of good news there. Be nice if everybody picked the correct answer. Clearly not everybody has, but at least everybody that's picked the wrong answer has picked the same one, so we can try to address why that is. Let's look at this. We want to find the direction of the magnetic field at point P due to these two bar magnets here. We know that the magnetic field, don't try to draw big magnetic fields like this surrounding it, right? We know magnetic field, you could do that, but it's not the easiest way to do it. We know that the magnetic field points away from north towards south. Now, eventually that's going to curve around here and, whatever, independent of this one, right? If this one's not there, it's going to look something like this, away from the north toward the south. It's going to curve away, but we're not really concerned about what happens out here. We're concerned about what it looks like at this point right here. So away from the north. Now let's pretend that one's not there. Let's put this one back in, take away this one. The magnetic field here points toward the south. Now in the end, it's going to come away from this north way over here, and it's going to go over to that south way over there, but we don't really care about that because we're just trying to find the field strength at that point P. So we get two magnetic fields. One is away from the first magnet, one is toward the second magnet. Now, as a result of both of these magnetic fields, we're going to get a magnetic field that's somewhere in between. It's going to look something like this, and that's going to be reflected in answer D. Now, the 5 people that picked answer A, the 21% of you that picked answer A, okay, which is incorrect, can anybody explain to me why you picked that one? There's got to be a reason, right? Because it wasn't just, oh, I don't know what I'm doing, I'm going to pick A. Everybody that got it wrong picked A. All right, thank you. So what you're saying is that you weren't sure what to do with this exactly. So you're saying that you got something at point P, it's going to kind of be attracted to the North Pole, and it's going to kind of be attracted to the South Pole. So in the end, it's going to end up being attracted somewhere in between. Okay, fair enough. Okay, fair enough. That's not actually terrible logic. It's wrong, but it's I can understand where that came from for sure. What you got to remember here is that point P is not a thing. Point P is a point. So you're not trying to find the effect on something here. You're trying to find the field strength there independent of an experiencer. So there's not something there that's attracted to or repelled by or anything of the sort to this north or south. It's a point in space where the magnetic field is in a certain direction. Just like, hey, here's a point in space right here. The Earth's gravitational field points downward. Now an object will move downward there, but there doesn't have to be an object there to say the gravitational field is pointing downwards. That make sense? So independent of anything that's there, which way does the field point? The field point there going to point upwards. It's going to point to the right, so it's going to be up and to the right. So good? Yeah. All right, I got one more for you guys. This one's number 69, also in your booklet. We'll also have you submit this one as number 1. But before you take a look at it, I want to just draw your attention to something. It didn't photocopy real well, so I want to make sure that you understand exactly what it's trying to say here. We've got a wire here. We've got electrons going through the wire. Okay, if this says electron current, then we're going to use our left hand, right? If it says conventional current, we're going to use our right hand. It's rare that it's going to say conventional current, but just in case, just so you know. We've got 4 compasses here. The 4 compasses all have a needle pointing outwards. That's kind of hard to see in these photocopies. In the originals on the diploma exam that this actually appeared, it was much clearer. So you wouldn't have to worry about that on a real diploma exam. It just doesn't photocopy real well. Again, all 4 compasses are pointing out of the page here. We want to know which compass is correct, which one is supposed to be pointing out of the page. All right, guys, a little bit more scattered on this one. We still have the vast majority of you answering one option, which is option C here, but we have a number of you picking option B, and then we have a small number of you picking option A as well. So we got A, B, and C. None of you picked D, which means we hope that D is not the correct answer. What do we got to know here? Two things in this question. First of all, we've got to know that a compass will point in the direction of the magnetic field. A compass will point in the direction of the magnetic field. The second thing we got to know is how to find the direction of the magnetic field that's caused by this wire. Oersted said almost 200 years ago that electric currents generate magnetic fields. What's the direction of the magnetic field surrounding this wire? And which way does a compass point in that magnetic field? So let's figure out what direction the magnetic field is first. Thumb in the direction of the particle, which is up the page. Left thumb because it's a negative particle. Fingers are going to point, well, to the right of it. My fingers point out of the page. To the left of it, my fingers would point into the page. In front of the wire, my fingers would point to the left. And behind the wire, my fingers would point to the right. Which compass agrees with what I just observed here? Which compass is pointing in the right direction at its location? Is compass number 1 over here to the left of the wire pointing into the page? No, it's pointing out, so that doesn't work. Compass number 2, in behind the wire, the compass needle should be pointing to the right because that's the direction of the magnetic field. It's not, it's pointing out of the page. Compass number 3, it's pointing out of the page. Well, to the right of the wire, the magnetic field should be pointing out of the page. So that looks like it's correct. And finally, number 4, we'll just make sure that we haven't made a mistake there somewhere. Number 4 is pointing out of the page. Well, in front of the wire, it should be pointing to the left of the page. It isn't. So option C is correct. And 80% of you got, or 79% of you got option C correct. So that's good. Good. Before we do a third hand rule, let's spend just another quick moment reviewing the second hand rule. First one, remember, was the wire grasp rule. Thumb in the direction of the particle, fingers point in the direction of the magnetic field that's caused by that moving charged particle. Second rule was the coil rule, where we had a solenoid or a coil of wire wrapped around something. Maybe you had an electric current going, this would be counterclockwise in this case. Looks like this, right? Leaving the negative end of the battery, going around to the positive end of the battery. Which way is the magnetic field? What's the polarity of this new electromagnet that's just been made? Well, if our coil has the current going down in the front, then we're going to stick our fingers down in the front. Not our fingers, our fingertips, okay? Fingernails down in the front. Which way does my thumb automatically point when my fingernails are going down in the front? My thumb is pointing to the left, right? So that means the magnetic field inside the coil is pointed to the left. That makes this end of the coil what? North or south? Did I draw backwards? Which way did they say it was? Oh, to the left, yeah, you're right. That makes this end of the magnet what? North or south? North. The magnetic field inside the coil points toward the north, away from the south. Outside, it would point from north to south, which is usually the way we look at it, just not in this context. Good? The method that we go through for all of these is pretty much the same, so I'm not sure if you understand this. I'm not sure that there's any value in going over another question. If you don't, then we'll do another example. Great? Okay, what I want to do now is introduce a third hand rule, the third and final hand rule. We're going to call this one the hand rule for deflection. want to draw a little picture here first. Let's say we've got a magnet over here with a north pole and a magnet over here with a south pole. There's going to be a south pole down here and a north pole down here, just not relevant to the question. There is a magnetic field surrounding this that's curved and looks like this, whatever. We're not going to worry about all of that. We're going to worry about just the magnetic field directly between those two magnets. Again, there is the rest of the magnetic field. It's just not relevant to this question. We'll see why in just a second. So this is what we're going to call our external magnetic field, our magnetic field that's just there. It's caused by some external factor like a couple of magnets. Maybe it's caused by the Earth. Maybe it's caused by, doesn't really matter. Okay, it's caused by something other than what I'm about to show you. Now, what am I about to show you? I'm going to take a negative particle and I'm going to move that negative particle through that magnetic field. So negative particle moving down the page, magnetic field pointing towards the right side of the page. Right, John? This charged particle generates its own magnetic field. That's the first thing that we learned about the relationship between electricity and magnetism, right? Moving charges generate a magnetic field. So we got two magnetic fields here. We have the magnetic field that's caused by the moving negative particle. That's the Ørsted discovery in 1819. But we also have the external magnetic field, the red magnetic field, the one that was caused by something else, in this case, these magnets. Two magnetic fields. Whenever you've got two magnetic fields, there's going to be an interaction between them. They're going to affect each other. There's going to be some kind of attraction or repulsion or something. There's going to be this interaction. What does that interaction look like? Well, here's where the hand rule for deflection kind of kicks in. We're going to use this rule to determine which way this particle is affected. Is it attracted? Is it repelled? Is it something else kind of in between attraction or repulsion? Which way is the force on this moving negatively charged particle? Here's how the rule is going to work. Once again, with your left hand, since it's a negative particle. If it was a positive particle, you use your right hand. So left hand. Everybody take your left hand. Shake it a little bit. Okay, ready? Okay, move your thumbs around. Exercise that up a little bit. Okay, good to go? Oh, is this too, are you too good for us? Like, can't do this? Can't participate? Pardon me? Okay. We got a thumb in the direction of the particle, which is toward the bottom of the page. Okay, just like with the first rule, the wire grasp rule, your thumb goes in the direction of the particle. That's unlike the coil rule, right? The coil rule is opposite. The coil rule, your thumb pointed in the direction of the field. But for the first wire grasp rule, thumb was in the direction of the particle, and we're back to that. Thumb in the direction of the particle. So thumb down the page. But in the first rule, you clenched your fist. Not necessarily tight like this, but you bent your fingers a bit at least. This time, you want to keep your fingers straight out, perpendicular to your thumb. So just like this. Kind of like you want to give somebody a high five. Thumb in the direction of the particle, which is down the page. Fingers are going to point in the direction, be careful here, not of the field that's caused by the moving charge. Okay, that would be this. Okay, if you wanted to find the field caused by the moving charge, you'd go thumb, bend your fingers. Okay, when we stretch them out, they're going to point in the direction of the external field, which is towards the south. So thumb down the page, fingers toward the right side of the page, palm is going to point in the direction of the force. Now, for me, that palm is pointing toward the front of the room because of the way my page is oriented vertically, right? For you, if you have this drawn on your page, your thumb is going to be pointing towards the floor. For both of us, our palm is pointing into the page. Does that make sense? All right, mine's pointing towards the front of the room, but that's into my page. Yours is pointing towards the floor, but with the way your page is oriented horizontally, that's also into the page. So the magnetic force here on this moving charged particle would be into the page. That's weird, right? We got a field that's pointing to the right. We have a particle that's moving down the page, but yet we have a force that's not to the right or left or down the page or up the page, but rather into the page? Yeah, it is weird, but it is what it is. The magnetic force on the moving particle will be perpendicular to both the movement of the charge and the external field. Okay? Thumb in the direction of the particle, fingers in the direction of the field, palm points in the direction of the force. Now, does that mean that particle is all of a sudden instantly going to change direction and go into the page? No. It's going to experience a force into the page. It's moving to the right, it experiences a force into the page, so its path would be more like this. Right? That makes sense? But it experiences a force this way into my page. Okay? It's moving this way, so it's going to kind of go in between like this. All right. Got a little bit of notes there. You can write down what you need to write down from that, and then we'll do a couple more examples for all of you to kind of master this second rule here. Let's take a look at a couple of examples here. I want everybody to do this. Follow along with me, please, okay? Take your left hand out, take your right hand out, because we're going to use both of these here, okay? We've got a charged particle. It's a negatively charged particle going towards the back of the room. An electron, maybe it's a chlorine ion, whatever. It's a negatively charged particle going towards the back of the room. We've got an external magnetic field that's caused by something, whether it's big magnets or whether it's the earth or whatever, it doesn't matter. It's pointing towards the right side of the room. So we've got a negative particle going towards the going towards the back of the room. We've got a magnetic field pointing towards the right side of the room. I want to know what direction that magnetic force is. Everybody do this with me, please. Everybody. Okay, you can watch me, and you might be able to do this yourself later on if you watch me. If you do this with me, okay, then you will be able to do this yourself later on. So thumb towards the back of the room, because that's the direction the particle is moving. Fingers stretched out, right? We only bend our fingers if we don't have an external magnetic field. We only bend our fingers if we're trying to find the field caused by the moving charge, or we're doing it with a coil. This is not a coil. This is not trying to find the field caused by the moving charge. This is trying to find the force when we've got the external magnetic field. So thumb towards the back of the room, stretched out fingers towards the right side of the room, palm's going to point downwards towards the floor. So we'd say in this case, the magnetic force is down toward the floor. Okay, another one. We've got a alpha particle, which is positive, right? Alpha particle. It's going towards the left side of the room, right over here. We've got a magnetic field pointing towards the ceiling. Right thumb towards the left side of the room. Fingers toward the ceiling. Which way does my palm point? Towards the front of the room. So the magnetic force would be towards the front of the room. Make sense? Okay, let's try another one. Let's say we've got a proton moving towards the back of the room. Let's say we've got a magnetic field pointing towards the right side of the room. Right thumb towards the back of the room. Fingers stretched out, not bent, right? Stretched out because it's the third hand rule, towards the right side of the room. Palm's going to point upwards. Got it? Okay, let's try this one. This one's a bit of a trick. Okay, so bear with me on this, okay? We've got an electron going towards the right side of the room. Sorry, the left side of the room, that would be. We've got a magnetic field that's pointing towards the right side of the room. So particles moving this way, magnetic field's pointing this way. Which way is the force? John? There is no force. It's a trick question. There is no force. This hand rule works only if the field and the particle's movement are perpendicular to one another. So in other words, one's moving to the right, one's moving towards and the field is toward the back of the room. Or the particle's moving upwards and the field is towards the left side of the room. If they're perpendicular, the hand rule works. If they're parallel, the hand rule doesn't work. But the good news is, it doesn't matter if the hand rule doesn't work because there is no force. If the particle is moving this way and the field is this way, the force is 0. You don't need to do a hand rule when there is no force. If the particle is moving this way and the field is this way, there is no force. Don't need to worry about a hand rule when there is no force. Now, if the particle is moving this way and the field is this way, no problem. We can use the hand rule for deflection, right? If the particle is moving this way and the field is this way, the bad news is it's a little bit trickier. The good news is we don't have to know that in Physics 30. You will have to know that if you take another course of physics sometime in university. But in Physics 30, we have to be aware of what happens here and what happens here. When they're perpendicular, you use the hand rule for deflection. When they're parallel, there is no force. Done. So it's either the force is 0 or it's use the hand rule to determine the direction of the force. That makes some sense? All right. Not only can we determine the direction of the force, but we can also determine the magnitude of the force. So for the first time in this unit, we're going to actually do a calculation involving magnetic field, magnetic force. The magnetic force acting on a moving charge as it goes perpendicular through a magnetic field, right? Not parallel because there is no force, not at 30-degree angle because we don't know how to deal with that. But when the charged particle is moving perpendicular to the field, here's the equation. Fm is equal to, I'm going to make this a little bit bigger so you can see that better. Fm is equal to QVB. So Fm would be the magnetic force. It would actually be the magnitude of the magnetic force because the direction isn't going to be found by this equation, right? We're going to use the hand rule for that. The magnitude of it. Q would be the charge, write this down. Q would be the charge of the particle that's moving through the magnetic field. That's going to be measured in coulombs, although it'll often be given to you in, say, like microcoulombs or nanocoulombs or something like that. You just have to convert that. V is going to be the speed of the particle, and that's going to be in meters per second. And B is going to be the magnetic field strength. And that's going to be measured in Tesla. Now, I want to ask you one little thing here. Little upside down T between the V and the B. What do you think that means? What do you think that little upside down T means? Lewis? Right. It's telling you that this equation is only valid if V and B are perpendicular to each other. If they're parallel, the equation is not valid. But that's okay because the force is 0, so you don't need to use an equation to find a 0 force. If they're not parallel and they're not perpendicular, then there's some other angle like 27.3 degrees or whatever the case may be. You don't need to worry about that yet. That's a first or second year university thing. Let's see what we can do with an example on page 599. This is an electron. Hey, that's important to me. I'm going to circle that because I want to remind myself that this is a negative particle, and if I'm going to use a hand rule, it's going to be a left-hand rule. Either wire grasp rule, left hand, coil rule, left hand, or a hand rule for deflection, left hand. Left hand, bottom line is left hand because it's a negative particle. It's traveling at this speed, perpendicular. Oh, okay, good. Whew. Right away I see that word perpendicular, and I breathe a sigh of relief because I know what to do when they're perpendicular, right? To an external magnetic field of 2.2 times 10 to the negative 1 Tesla. We want to determine the magnetic force. So magnetic force includes magnitude and direction. We got 3 hand rules, right? There's the wire grasp rule. There's the coil rule. And there's the deflection rule. The wire grasp rule is used to find the magnetic field produced by the particle. That's not what we're trying to find. Okay, we don't really care what the magnetic field looks like surrounding this negatively charged particle. It has one, but that's not what the question is asking. We don't have a coil of wire at all, so clearly it's not going to be the second rule. The third rule, the rule for deflection, is the rule that allows us to find the magnetic force given the external magnetic field. So that's what we're going to use here. Let's find the direction first. We're going to say thumb into the page. I know they're trying to draw this in 3 dimensions, and that confuses people a little bit sometimes, but that's what they're representing here, into the page. So we're going to say thumb into the page. Fingers go in the direction of the field, which is from north to south. Palm is going to point which way? Don't say up. Okay, because if your page is horizontal on your desk, it's not up. Okay, if your page is vertical like mine, then it's up, right? What we're going to say toward the top of the page, or you could say up the page, but don't just say up, right? Okay. Relative to the page, it's toward the top. Now, let's figure out what the magnitude of that force is. Well, if they're perpendicular, then the equation that we just learned is valid. So there shouldn't be any issue here with solving this. Notice we're dropping the sign of the charge. We always do, even though it's a negative charge. We needed that to determine which hand rule we use, but in the equation, we're just going to make it positive. V is 3.20 times 10 to the 5 meters per second, and B is 2.2 times 10 to the minus 1 Tesla. And we should get 1.13 times 10 to the minus 14 newtons. Is that good? 1.13 times 10 to the minus 14 newtons. Pretty small force, but we're also talking about not an incredibly strong magnetic field, and we're talking about a charge that's only 10 to the minus 19 coulombs. Would this be deflected? Yeah, it's a small force, but we've got a ridiculously small mass, so it doesn't take much force to deflect such a small mass, right? Okay. All right, here's what I want you to work on now. Obviously, questions that go along with this on page 599, or at least one of the questions. I don't want you to do question 2, actually. Why not? Why am I scratching at question 2? We got 30 degrees. We don't know how to deal with that. We don't have to know how to deal with that. Perpendicular, F is equal to QVB, hand rule for deflection. Parallel, force is 0. 30 degrees, who knows, who cares right now. Do question 1. In addition to that, I'd like you to have a look at your worksheet, number 11. And work on that for homework, please.